All right, so we did constant function. Identity function, it has the equation of the form y equals x, right? And why is it called identity? Because whatever x is, y is the same value, right? And now, from this y equals x, right, we can embellish that and we can derive other forms of that equation. So y equals x it's a linear equation, and it gives you, right, a line. And so from that, we can derive functions such as f of x is equal to, let's say, negative 2 over 3, x minus 1, etc. All right? So that's where your linear functions come from. They're called identity functions. That's their parent function. Okay, we have the quadratic function. We know that. That's a parabola. We're all experts on graphing parabolas now. Okay? Cubic function. Okay? All right. So notice for the cubic function. Okay, so here are some things that I want you to know. Let's go back to the parabola, right? The parabola has the form x squared. That means whatever value x is, y is going to be the square of that, so it's going to be positive, right? So whether x is a positive number or a negative number, the square of it will always be positive. That means whether you put in positive 2 or negative 2, you're going to have the same value of positive 4, right, for your y. Also, it means if it goes up on the right side, it should also go up on the left side, right? They have to be facing vertically the same direction on the right and left because they're squared the same way. Cube, though, take a look at what happens. If I put in a positive x value, the cube of it is a positive number. But if I put in a negative x value, the cube is a negative number, right? So whereas the parabola was an even function, this is going to be an odd function. That means their end behaviors are opposite, right? So that's one thing I need you to know, is that for the x cubed, it goes up on one side, but down on the other side. For the x squared, faces the same direction on both ends, okay? So both ends face same vertical direction, ends in opposite vertical direction. Okay, square root. What's the deal with the square root function? All right, so the square root has a special requirement, right? What's that requirement? Question or answer? Yeah.
It cannot be negative.
What can't be negative?
If your x value is negative, it's an undefined number and it won't be real. So
right.
There's only going to be stuff on the right.
Exactly. So if I have y equals the square root of something, that number inside, first of all, what is that called? If this is the radical symbol, what's the stuff inside called?
The radicand.
The radicand. Okay, so the radicand must always be greater than or equal to 0. Okay, so by definition then, the square root function can't exist over any values of x that makes the radicand negative. Okay, so it can only exist on values of x that makes the radicand positive. So exists only on x values which make radicand positive. Huh? Well, okay, so root x, the parent function, yes, it's in, positive x and positive y. But if it was shifted left or right, then that would change, right? Now, what else? What happens as x gets progressively larger? Y also right, y also increases. Not exponentially, but it increases. Okay? Right, but that's not exponential. Exponential is if it was 2 to the x, right? So it increases like the square root of x. Okay? So that's important. Okay, so these are the things that I need you to know. As x gets bigger, yes, the y values are going to get bigger. Slowly but surely, they're going to get bigger. Okay? All right. Let's talk about the reciprocal function. This is one of my favorites. Okay? Reciprocal function has the equation f of x is 1 over x. So first of all, just looking at 1 over x, what values can x not have? 0, right? So x can't be 0. Okay, so let's look at y. Okay? If x is positive, is y positive or negative?
Positive.
Positive. So when x is positive, y is positive above the x-axis. When x is negative, where's y? Negative below the x-axis. Okay? Now, can y go up to infinity? Can the y values increase to infinity?
Yeah.
Yeah. Can the y values, can the y values ever be 0?
No.
No. All right, so think about that. Is there a value that you can plug in for x that makes the y value 0?
No.
No. So these are the types of things that you need to be looking at. When you are on that, desert beach stranded, right? And you have a function that you have to graph. Okay, you look at it and you go, okay, what is this function doing for large values of x? Oh, it's going to 0. Oh, it's going to positive infinity. Okay, when is this function 0? Never for this one, right? So these are the sorts of things that we need to be looking at. And then eventually we're going to talk about horizontal asymptotes, vertical asymptotes, and just sort of formalize it all, okay? All right. Yes. Yeah. Since we're talking about asymptotes, where is there a vertical asymptote here?
0. F of x equals 0.
There is a vertical asymptote at x equals 0. And then there is a horizontal asymptote
At y equals 0.
at y equals 0. Okay? All right. Let's talk about the absolute value. Right? We all know absolute value looks like this, and we like mindlessly do a V, right? But if you look at it closely, look at this. This is actually a piecewise defined graph, right? It has two regions here. There is one region where x is greater than or equal to 0, and then there is another region where x is less than 0. In the region where x is greater than or equal to 0, take a look at what is being graphed. That's y equals x. In this region, take a look at what's being graphed. Y equals negative x, right? So that's what it looks like. If you look at it even more closely, right? This is the graph of, what is this the graph of?
Oh,
Y equals x,
Identity.
right? This is y equals x. So now, if I were to go and put an absolute value around the x, what am I doing? I'm saying, okay, yeah.
I'm just saying, you're getting rid of all the negative.
You're getting rid of all of the negative what values?
Negative y.
X or y values? Y values. Can x still be positive? Yeah. Can x still be negative? Yeah. So it exists overall here, but can y ever be negative now? No. So what it does is it takes the part which was negative and reflects it up this way. Okay? Okay. So I said that the reciprocal function was one of my favorite. Okay? Here is another one of my, this is probably like the favorite one of mine. We cover it less and less and less now, but I always want to at least mention it because I feel like, I owe it some credit. It's such a beautiful function. This is the greatest integer function, right? greatest integer function, first of all, look at how it looks, right? Look at how the graph looks. What are the y values? What is the domain? I'm sorry, what is the range?
No, it's not. It's like a set. It's
Wait, let's raise it. It's just integers. It's just integer values, right? There's a graph at, like 4, 3, 2, 1, 0, -1, -2, -3. So the range is just integers. Well, what about the domain? Take a look at the domain. What's the domain? All real numbers, because look, where one is open, another one picks up, and another one, and another one, and another one, and another one. So the domain is all real numbers, but look at how it looks here. When x is 1, how much is y? 1. When x is 1.1, 1. When x is 1.2, still 1. 1.9, still 1. 1.999, still 1. Okay? For the whole time that x was from 1 to 1.999, y is 1. What happens when x is 2?
Y is 2.
Y is 2. And then for the whole duration that x is in the 2's, y is 2. Okay, so it's always the greatest integer, like right below it. So for example, do you see what I mean? Yeah. So it's written like this. Okay. All right. So let's talk about some transformations. Okay, you've done many examples of transformations in algebra 2, yes? Okay. So a transformation is basically something that affects the appearance of the graph. It shows up in the equation. First and foremost, a translation basically shifts the graph up or down or right or left. Okay? Also right, left. Okay? All right, let's talk about vertical and horizontal translations. I know you guys know this. So if I have f of x and I add a number to it, plus k, then that affects it, it moves it either up or down. So for example, if this is y equals x squared, what would be a possible equation here for that green one?
Y equals x squared plus 3.
Thank you. Go ahead and raise your hands. What would be one for this one? Yes.
Y equals x squared minus 3.
Correct. Okay. All right. So now, again, if this is y equals x squared, what would I do for this green one? Somebody raise your hand. Tell me, what would I do for this green one? Yeah. Mm-hmm. Minus, right, x minus 2, let's say, squared. Okay? And so for this one, it would be y equals x plus 2 squared. So how do we know what the shift is? You take the stuff inside the parentheses, x minus 2, set it equal to 0, x equals positive 2. Positive 2 means you go to the right. Okay? Huh? Okay, so let's do some of these.
So much easier to memorize an equation.
Yeah, we do not memorize. We understand. We do not memorize. We're going to graph these by hand. We're not going to graph them with a calculator or anything. All right? So it says use the graph of f of x equals x cubed. Okay, so let's just graph x cubed for a minute. All right, x cubed. Let me have a starting point. When x is 0, what's y? 0. I'm just doing x cubed, the parent function, x cubed. Okay, so now, what this function does is it takes the y value, it takes the x value and does what to it? Cubes it. So, if I go over to the right one space, I'm going to go up like the cube of 1. All right? So, if I go over one space, I go up 1 cubed, which is 1. Okay? That means if I go over 2 spaces from my center, I go up how much? 2 cubed, 8. Okay, so I go up 2 cubed, 8. All right, and now I know that if I went to the left 1 space, I'm going to go down 1 cubed, 1. If I went to the left 2 spaces, I'm going to go down 8 spaces. So this is how my parent function looks. Okay, you're not going to have to draw these parent functions every single time. We're just doing it this one time. Okay, so now let me go and graph g of x. So I'll label this f of x. Let's graph g of x now. Where is that center? What happened to that center point for g of x? Okay, I'm assuming you said it moved down 3 spaces. It moved down 3 spaces here. And now from there, the mechanism of x cubed is the same. That means if I go horizontally 1 space, I go up 1 cubed, which is 1 here. Okay, and it's mirrored like that because it's an odd function. And now if I go over horizontally 2 spaces, how much do I go vertically? 8, right? It's always the same. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, now here, right, I know that if I went over 2 spaces here, it's going to go down to like -11. So just know that, you know, in order to make it plausible, we're not going to pass that -3 space, right? So that's how it looks. Do you see that? Did I put anything in the calculator? No. Did I make a table of values? No. These are tedious and monotonous, and we're not going to do that because it doesn't show understanding of what this mechanism does. All right, so let's do this one a little bit more quickly. We're going to move right 4 and up 2, so we're going to go over to 4 and 2. And again, this is an x cubed, same mechanism. Horizontal, if I go over horizontally 1 space, I go up or down 1 space. If horizontally I move 2, I need to go up and down like the cube of 2, 8. Okay, so from 2, I'm going to go up to 10 and -8. Okay, do you see? This is what we do. We're not going to do anything else more mundane or anything. All right, so here we go. Reflections on the x-axis are done by a negative in front of the function. Okay, and that just reflects it. It doesn't flip it horizontally. It reflects it around the x-axis. And then if there is a negative inside, it reflects it around the y-axis. All right, so let's do these. Again, we're going to do the parent function. Just once we're going to do the parent function because I want to show you how to do it. When x is 0, y is 0. And I know that it's a root x, so it's only going to exist for certain x values. If I go over 1, I go up like the square root of 1. Okay? And now, because I'm going to take square roots, if I go over 2, I go up like the square root of 2, but that's silly. That's like 1.2, and I'm not going to deal with that. So I pick values for which I can take square root. So if I go over 4 spaces, I could go up 2 spaces. If I go up 9 spaces, if I go over 9 spaces, I go up 3. So do you see that? It is increasing surely but slowly, okay? Slowly but surely. Okay, here. What happens? What does the 4 do? The positive 4. Moves it up 4, and what does this do? Okay, one more time. We're not going to use the word flip. It's a reflection around the x-axis. Okay, I do ask on the test for you, or the quizzes or the test, whatever, for you to actually like write in words what's happening. Okay, so there is a reflection in the around the x-axis or in the x-axis, and there is a vertical shift 4 units. Okay, so we're going, okay, so we're going up 4, 1, 2, 3, 4, so that's where we start. And now, and it's the same thing, if I move over 1 horizontally, I gotta move vertically 1 space, but do I go up or down? Down. If I go over 2, or if I go over 4, 1, 2, 3, 4, I go over 2 units, okay? If I go over 9, I go down 3 units. All right, so that's what g of x, or h of x looks like.
You want us to write it on the problem?
So normally you're only going to graph like h of x.
No, I'm talking about when you ask us to write what's happening from the graph. You want us to write it right below the equation?
So what if you have the square root of negative x? Is it impossible to have a negative? Well, you just have to make sure that the values of x you put in make the entire integrand positive. So, can x be positive 1? No. Can x be negative 1? Can x be negative 2? Negative 3, negative 4. So here x will exist only, the graph will exist only here, right? That's why it's a reflection on that side. Do you see how beautiful it is? Like, because you physically cannot plug in a positive value for x. So it has to live on that side. Isn't that beautiful? Like, do you see why I love math, right? It's because no matter what you think should happen, the functions and the mathematics of it will always hold. It'll always keep you in check. Okay? Yeah.
So if we just put a negative sign on the outside of that, it would go left and
it would go left and down like that. Isn't that cool? Even cooler. Okay. Huh?
And then if you make it plus or minus,
and then if you do plus or minus, it's even worse. Yeah. Okay. So let's do this one. We're gonna go up to the right, to the, which way? 1.
Yeah.
Left and down. And this is a reflection. So negative 1 and 2 here. All right, and it's a reflection, meaning, again, same thing. If I go over 1 space, I go down 1 space. But if I go over 4 spaces, I go down 2, and so on. And so that's how it looks. Okay? Have we used the calculator anywhere here? No, right? Because we understand what it looks like. All right? So, now then, let's talk about dilations. Okay, vertical and horizontal dilation. So let's talk about vertical dilations. First of all, a vertical, if something is expanded vertically, it means, imagine this blue parabola had strings, right, attached here and here. And now imagine if I pulled up on those strings, right? It would get narrower, right? Yeah. Whereas if I were to like push down, right, then what would happen? It would get wider, it would bulge out. So that's why, when we say expanded vertically or compressed vertically, that's what we're talking about, okay? So the top is, the green is expanded, the bottom is compressed. Okay, but that's fine. But you know what? Nobody's sitting up there, doing, compressions and stuff. What is happening behind the scenes? Let's talk about what's happening behind the scenes. So suppose your parent function here is y equals x squared, right? What happens if you go over 1 space? How many do you have to go up? 1 squared. So how much? 1. If I go to the right 2 units, how much do I go up? 4. And then if I go 3, how much do I go up? 9. The square, okay? Y increases like the square of x. This is the technical terminology. Like at the math parties, that's what people will say. Yes, y increases like the square of x, okay? Now, what if I had this function, y equals 2x squared? Now, it's still a parabola. It still holds true down like to the bone marrow. It's still, if it goes over 2 spaces, it's got to go up like the square. But now, it goes up 4, and then in addition, it's multiplied by 2. Okay? Do you see what I'm talking about? So, if it goes over 2 spaces, how much will it go up? 8. Because not only is it squared, but it's also multiplied by 2. Does that make sense? Yes or no? What if you had y equals 1/2 x squared? If I go over 1 space, how much do I go up? How much would I have gone up if it was x squared? 1. But now it's half of that, so how much do I go up? 1/2. If I go over 2 spaces, how much do I go up? 2. It would have been 4, but now it's half of that. So that's how it works. So this, it's sort of like it impedes the process. Okay? All right, so take a look at what happens here. Take a look at what happens here. What if you have y equals 3x squared? What happens now? That's what happens. If you go over 1 space, okay, so go over 1 space horizontally, okay, the function multiplies that by 3, then squared. It multiplies by 3, then squares. So do you see the difference between vertical and horizontal dilations and compressions? Okay? Whereas this one, it's like molasses. Like you try to go over 2 spaces. So suppose this is y equals 1/2 x squared. You try to go over horizontally 2 spaces, it holds you back. It multiplies by 1/2 and then it squares. Okay? All right. So let's do some of these. Okay. This is an absolute value, right? But now there is a vertical, there is a reflection. And what does this 4 do? Right. So this is what is this? It's a horizontal dilation. Okay. So at 0, what's y? 0. So now look. If I try to go over 1 space, it multiplies by 4 and then moves me down. Right? So I go down to what? -4. And here. Because it's linear, 1 point is good enough. Okay? All right. So go ahead and do this one. I'll give you, I'll give you like a minute to do B. I'll pause this for a minute. 1/4 x squared. All right, so let's do some piecewise. I'll do that first one with you guys. All right, so here we have partitions at 0 and 3, right? So the first thing I do, I'm going to graph that first one. I'll color code this. So this one, I'll do it in red. I first plug in 0 in here, right? At x equals 0, I'm at 3. Is that right? And is it open or closed? Open. And now, what does that look like? What is that? What kind of equation? What kind of graph? quadratic, cubic, constant, identity, what? Identity, and it's got a slope of what? -1. That means from left to right, is it going down or is it going up? Down. It's going down, right? With a slope of 1. So I kind of work backwards and I go, okay, the relationship has to be 1, 1. So up 1 over 1, but I go backwards. Up 1 over 1, and that's how that looks. That open circle doesn't have to be that big. I just do it like that in order to emphasize it. And when you're doing it, make sure it's clear and I can see it. Okay, so number 2 goes from 0 to 3. Luckily, that's also what kind of graph? Identity. So 2 points should do it, right? And I plug in 0 and I get 0. And then I plug in 3 and I get what? 6. That's open. And then I connect. Then I've got a square root. Okay? I plug in my 3 and I get what? At 3, it's how much? 2? Right. And then I try to find another point that's going to give me a perfect square underneath. So for example, when x is 8, right? I have a 9 underneath, right? When x is 8, it's 3. Okay? I always try to do like those integers. I always try to come up with integer values because it's easier for me to graph. Okay, who wants to deal with like, little random numbers? Okay, go ahead and do B.
I graph it.